Thus we can write I is equal to half integral minus infinity to infinity f of x dx, or it is half minus infinity to infinity x square over x6 plus 1 dx. Okay. So the point is that we have to evaluate this integral. Either we can use the method available in real analysis. If the method is not available in the real analysis, then we can use the residue theory here. Let us see how we use this residue theory here. We will follow the few steps. Step 1 is, after looking at the integral, if the integral is from minus infinity to infinity, there is no need of making it finding whether the function is even or not. If the integral is from 0 to infinity, then we have to make its integral from minus infinity to infinity by looking at the integral whether the function is even or not. Okay. So as a first step, we will see whether the given function is even or not. This first step should be followed only when the limit is from 0 to infinity. Okay. So check f of x to be even or not. Even or not. And this, as I said earlier, this step is only useful when we have a limit from 0 to infinity. And then make it, if not, if even, then make the necessary changes, make the necessary changes, whatever you require in the limits, changes in the interval of integration. Okay. As a step 2, instead of f of x, consider the function f of z, so that for y is equal to 0, we have f of z is equal to f of x. So what we do, we directly replace x with z in the given function. Hence f of z is equal to z square over z6 plus 1. As z is equal to x plus iota y, and when we put y is equal to 0, z and x both are equal. So instead of considering f of x, we consider this function, which is a function of z now. I think it's easy to change the function. Just replace x with z. So this is the second step. Okay. As a third step, thus instead of evaluating the principal value of the integral, this one, what we do, we evaluate the contour integral f of z dz over the contour C, where, so you can say here as this step 3, okay, step 3, you can make it step 3, where the contour is defined, the contour C is shown below. That is, we consider this x-axis, this y-axis, and we take 2 points minus r to r, minus r to r, it's okay. What we have to do over for the principal value here, we have to integrate the integral from minus r to r. So that means we have to follow this path from minus r to r. We have to follow this path. We have to integrate the function along this line from minus r to r. So to use the residue theory, we need a contour, closed contour. So what we do over here, we make it close by considering a semicircle CR. Okay, so we have made it closed by going from minus r to r and then along CR coming back to minus r. Now this is closed contour. Okay. So this contour basically C consists of two parts. C consists of two parts. Number one, CR union L, where L is the set of points from minus r to minus r to r. Okay, this is L. So this C consists of two contours, two arcs. One is CR and the other is L, straight line. Straight line consists of these points. So this thing to be noted here, whenever you are required to find the value of the integral from minus infinity to infinity, whenever you are given the interval minus infinity to infinity, you have to consider this type of contour. Okay.
इसमें अगर फंक्शन अवेलेबल है, फंक्शन एक्सपोनेंशियल फॉर्म में है, तब भी
अगर तो इंटरवल माइनस इन्फिनिटी टू इन्फिनिटी है, तब भी ये होगा. We will consider that function as again separately. So this is the contour. Then after that we will see how many singularities of the given function lies inside the contour and how many singularity lies outside the contour. This is step 4. Step 4 is find the singularities of the given function, given f of z. For example, if f of z is equal to z square over z6 plus 1, then there are 6 singular points, 6 singularities. Singularities are singular points. 3 of them lie inside the contour shown in the figure, and 3 of them lie outside the contour. How we can find the singularities? We will solve this equation z6 plus 1 is equal to 0 to find the singular points. Okay, so z6 plus 1 is equal to 0 means z6 is equal to minus 1. So there are 6 roots of minus 1. Okay, 6 roots of minus, you can say 6 roots of unity as well. So as said in the very beginning, that the roots of unity always form a regular hexagon, regular polygon within the circle. Regular polygon. If there are 6 singularities, one of them is w is equal to 1 and minus 1, and similarly other values minus 1 as well. So we will find that I think 3 singularities will be lying here. This here, this is 60 degree. So here, first one here, then 60 means 120. Okay, and then here, and so and so. So there will be no lying on this. No will lie on this line. What are the singular points? Let us see here. To solve this, I think one is at 90 because there is iota involved there. So one will be at 90 degree. If we have this unit circle, then one is here, one is at 30 degree here, and one is here, and one is here. These are the 6 singular points. 3 of them here will lie inside this contour, provided this r is greater than 1. If r is less than 1, this will go outside. Similarly, all these will go outside. These 3 will lie inside only when r here from minus r to r, this r is taken greater than 1, then 1, 2 and 3 will lie inside. And these are not lying inside. So we will consider only 3 singular points instead of 6 singular points. We are dealing only with the 3 singular points. Okay, for the given contour.